Assalamualaikum and hi everyone. My name is Nur Natasha binti Abdullah. My metric number 2x02x2. Okay, group project. Our group project is the method of Lagrange Multipliers. Okay, I would like to presenting about introduction. Okay, the Lagrange Multipliers method is versatile to widely applied in various fields such as physics, biology, finance, computer science, and also logistics. It proves invaluable in solving constraint optimizing problems by efficiently balancing multiple constraints and finding optimal solutions. It can shaping aerodynamics in aircraft designed to optimize investment portfolios in finance. Its applications extend to algorithm optimization in computer science and logistic management in supply chains also. Lagrange multipliers offer a systematic approach in making them indissipable and addressing the complexities of real-world scenarios across diverse domains. Okay, next I will explain about the background of the study, which is the first application we choose manufacturing constraints. Okay, constraint in manufacturing encompass both internal factors such as bottlenecks in specific work centers and inherent limitations in processes like fixed durations for chemical reactions impacting overall production efficiency and throughput. Okay, the second one is external constraints such as the persistent shortage of skilled workers pose significant challenges to the manufacturing industry. This shortage not only hampers production capacity expansion but also strains existing resources, hindering the adoption of advanced technologies and innovation practices. The third one is understanding and addressing manufacturing constraints are crucial for developing effective strategies to enhance productivity, streamline operations, and also navigate the complexities of the industrial sector, emphasize the need for proactive solutions to internal and external limitations.
In the world of transporting stuff from one place to another, making sure delivery truck use full wisely is super important. Big companies with lot of truck want to find smart way to make their deliveries both cost effective and good for environment. The big challenges is to figure out how to send this truck to different places while using the least amount of fuel. It's not just about filling up to the gas tank. It also making sure each truck is carrying the right amount of stuff without going over its limit. This demands the use of mathematical model and optimization approaches such as the use of Lagrange multiplier to find the most efficient distribution of cargo among different vehicle and destination. By addressing this complicated issue, the organization can improve operational efficiency, minimize environmental impact, and help to create a more sustainable and cost-effective transportation system. The key concept in this project revolves around the application of Lagrange multiplier to solve real-life problems in the domain of transportation and manufacturing. In transportation, to gain insight into minimizing fuel consumption for a delivery truck fleet while adhering the constraints such as cargo capacities and distance limitation. In manufacturing, to minimizing production costs while considering resource constraint. By using Lagrange multiplier into this real-world application, the project seeks to provide practical solutions that enhance operational efficiency, reduce costs, and contribute to the sustainable management of resources in transportation and manufacturing.
Hi, my name is Nur Afza binti Muhrin. My metric number 294488. I'm going to explain about the objective. Using Lagrange multipliers to reduce production costs in the manufacturing setting while negotiating the limitation of scarce resources is the focus of the study. Finding the best production quantities for various products is the goal in order to determine how well Lagrange multipliers work. For transportation logistics, in this instance, the emphasis is on delivery truck company that wants to use as little fuel as possible when moving cargo to various destinations. The goal of the research is to optimize the distribution of cargo among various trucks and routes. For methodology, the Lagrange multiplier method serves as a strategic tool for pinpointing local maxima and minima of a function f x y while adhering to constraint g x y. For the scenario under consideration, the optimization goal is to identify extreme values of xy constrained by the condition g of xy equal to k, where k is a constant. There is function f of xy equal to c, where c is any real number, and the objective is to determine the largest value of c at which the graph f of xy equal to c intersects with graph g of xy equal to k. The maximum and minimum values of f are then obtained by evaluating f at various points xy, where the largest value corresponds to the maximum value of f and the smallest to the minimum value of f.
On to the next section, which is examples and analysis. The first example I would like to present is minimizing the cost of production subject to resource constraint in manufacturing. Based on the question below, a firm manufactures a commodity at two different factories, factory X and factory Y. The total cost in ringgit of manufacturing depends on the quantities X and Y produced at each factory, respectively, and is expected by the joint cost function, which is C x, y equals to x squared plus xy plus 2y squared plus 200. If the company's objective is to produce 1,900 units per month while minimizing the total monthly cost of production, how many units should be produced at each factory?
First thing first, we need to know that the constraint that must be 1,900 units, which means x plus y equals to 1,900. And then we can form another equation, which is gxy equals to x plus y minus 1,900. And then we can form a Lagrangian function, which is L x y lambda equals to x squared plus xy plus 2y squared plus 200 plus lambda x plus y minus 1,900. Next, we do partial derivative with respect to x, y, and lambda. And then, from there, if we let equation 1 and equation 2 equals to lambda, it is true that 2x plus y equals to x plus 4y. Cancelling out x, y, and lambda, we will get a new equation, which is x equals to 3y. By using substitution method, we can see that y equals to 475 and x equals to 1,425. So if we use x and y into the C equation, we can get 3,158,950. After analyzing these examples, we can conclude that to minimize costs, the company should produce 1,425 units at factory X and 475 units at factory Y. Second, the minimum cost is found when for X 1,425 and Y equals to 475, which is 3,158,950 ringgit. For the next example, I will pass to the next presenter.
So we move the second example analysis, which is transportation constraint. So our example here is a delivery truck company with 3 trucks, trucks A, trucks B and trucks C, each with a distant consumption rate measured in miles per gallon, MPG, and cargo capacity restriction. So the purpose is to develop delivery routes that minimize the fuel usage, which is fuel consumption, and ensure each truck's load capacity is not exceeded. So we have truck information. Trucks A, fuel efficiency is 10 mpg, max cargo capacity is 2,000 pounds. Trucks B, fuel efficiency is 15 mpg, max cargo capacity 2,500 pounds. And lastly, truck C, fuel efficiency 12 mpg, max cargo capacity is 1,800. So last and destination and cargo demand. So the first one, destination is Bukit Kayu Hitam, which is labeled as Cape, requires delivery 1,500 pounds. Next, destination Changlun C, requires delivery 1,200 pounds. And lastly, destination Chitra J, requires delivering 1,800 pounds. So variable X is used to be amount of cargo delivered by the truck I to the destination. So this is the constraints. Cargo demands at each destination must be met, and each truck's cargo capacity must not exceed it. So the best ideas to do the example is firstly we have to do the objective function. So D is the minimize the total fuel consumption equation, x1 over 10, x2 over 15 plus x3 over 12. So by the using Lagrange multipliers, which take into consideration both cargo distribution, constraints, and fuel consumption. So this is our Lagrange function for the example for our examples, and by using the information given. Then we have to get the optimal value by using partial derivative with respect to xi and delta I. So next we have partial derivative respect to ai. We will equal to 0 for all, and for the respect to delta I, we will equal to 0 also. So from our earlier partial derivative respect to I, we make the delta 1, delta 2 and delta 3 as a subject. So as we can see our equation here, then we substitute the expression for delta I into the equation. So we will get as like this. So the solution is consistent. So when it is consistent, so it can use the minimization and Lagrange multipliers. So to find minimization of fuel consumption, after we get x1, x2 and x3, which is x1 is 2000, x2 is 2500, x3 is 1800. So we substitute to our objective function as we do earlier, and we will get the minimization of total consumption, which is 516.67 pounds. So next, we move to the analysis data for examples 2. Fuel efficiency consideration. So truck B, having a maximum energy and efficiency 15 mpg, received the heaviest transport load 2,500 pounds. This choice allows minimize total fuel usage. So next, cargo distribution. Each truck deliver a certain amount of cargo to fulfill demand at each destination. Third, our truck usage. So as we can see, truck A, fuel efficiency is 10 mpg, which is carries 2,000 pounds. Truck B, fuel efficiency is 50 mpg, which carries 2,500 pounds. And truck C, fuel efficiency is 12 mpg, carries 1,800 pounds. So for the total fuel consumption, is minimized based on A sign, cargo amount, and fuel efficiency of trucks. The minimum total fuel consumption, as we get earlier, 516 and 67 pounds. Cargo capacity, all trucks stay within their maximum cargo capacities, 2,000, 2,500 and 1,800 pounds for trucks A, trucks B and trucks C.
Look that the objective of cost production optimization is to minimizing monthly production cost while aiming for a target output of 1,900 units. The result in the optimal production strategy of manufacturing is 1,425 units at Factory X and 475 units at Factory Y. This strategic allocation led to a minimal total cost, then showcase the effectiveness of Lagrange multipliers in cost optimization. The objective of transport constraint is to minimize the total fuel consumption in a delivery truck company considering cargo distribution constraint and truck capacity. This one is allocated the heaviest load to truck D with the highest fuel efficiency optimization fuel usage. Each truck adhered to its cargo capacity constraint, resulting in a minimal total fuel consumption of 516.76 pounds. This highlights the practical utility of Lagrange multiplier in complex logistic and transportation scenarios. In both scenarios, the Lagrange multiplier method proved instrumental in providing systematic solution to intricate optimization challenge. This finding emphasized the method's versatility and applicability across diverse real-world scenarios, underscoring its significance in strategic decision-making for minimizing costs and enhancing efficiency in production and transportation process. That's all from me. Thank you.